All right, so now we're going to carry out an example where we're using a PFR that's carrying out multiple reactions. So the problem statement for this reaction says, the following reactions are carried out in the gas phase in a 400 cubic decimeter PFR at 325 K. And we're given a set of complex reactions, these three reactions shown here, and we're given data for the rate laws of the different reactions. Notice that they are not elementary. I guess one of them is, the other two are not. And we're given the data for the rate constants. This is going to be an isothermal reaction. We're not given any information about the heat of reaction or the activation energies, etc. And we're told that the reaction is being carried out at 325 K, so we're going to assume that that is an isothermal reaction. Okay, so for this reaction in this reactor, species A is fed at a concentration of 0.2 moles per cubic decimeter and an inlet volumetric flow rate of 100 cubic decimeter per minute. And what we need to do is plot the concentrations of A, B, C, D, and E in the reactor and then determine the selectivities, the total selectivities, or the outlet selectivities of D to E and then C to D. So I'm going to develop the equations to do that here, and then since this is a more involved problem that probably requires more equations than we can or than are allowed in Polymath Plus's free online server, I'm going to use Python to do that. Okay, so let's start out developing this problem solution, and I'm going to start out by writing the mole balances. So this is a multiple equations problem. I hence cannot solve this problem in terms of conversion. First of all, what would it be the conversion of? Would it be, we have several reactants. We have A, C, and D are all reactants. So which one of those would it be? Maybe there, A would be the obvious choice because it's the primary reactant. It's the reactant that's fed. It's involved in two of the three reactions. However, the issue with taking A as writing the problem solution in terms of the conversion of A is that, if we write conversion of A, it doesn't tell us how much of A is reacting via reaction 1. It doesn't tell us how much of A is reacting via reaction 2, and it tells us nothing of reaction 3. So it doesn't give us enough information. So when we have multiple reactions, we cannot simply condense the solution into this one equation in terms of X, as we have been able to do in a single reaction. This is because one equation doesn't give us enough information to solve for all of our unknowns. So we need to develop a solution with our solution set. Our design equations has to include the mole balances for all of the different species. So we're going to write down then the PFR mole balances for the different species. So that's going to be the mole balances in terms of moles. DFA dV equals RA. Similarly, we're going to say DFB dV equals RB. DFC dV equals RC. DFD dV equals RD. And DFE, that was written pretty sloppily, so let me redo it. DFE dV equals RE, where all of these different R's are the net rates. Okay, so now let's do the net rates. And in fact, I'm going to neaten up this solution a little bit. I'm going to say mole balances. And so then all of these rates are net rates. So now I'm going to write expression for net rates of each species. And specifically, these are net rates of generation. And that's because that's what I've written in the mole balances. The mole balances are all the net rates of generation. Okay, so now it goes back to how all of these different species participate in these different reactions. So for the net rate of A, RA, that's participating in reactions 1 and 2. So that's going to be R1A plus R2A. Now, A is a reactant in both reactions 1 and 2. So I'm writing here net rates of generation, or rates of generation for these two different reactions, but those quantities are going to be negative. And we'll get to that in just a second. Okay. Species B is only involved in reaction 1. Species C is involved in all three reactions, R1C plus R2C plus R3C. And again, if we go back and look, in the first reaction, species C is a product, and in the second two reactions, it's a reactant. So this quantity, R1C, is going to be positive, whereas R2C and R3C are going to be negative, and we'll take care of that in just a second. Right now, we're just going to write down the net rates. R2D plus R3D, and then RE is going to be equal to R3E. Okay, so that's our net rates of generation. Now let's write down our relative rates. So this is going to take care of both the signs on the rates in each reaction, as well as the stoichiometry. Okay, so we're given information here about if reaction 1 is written in terms of species A, reaction 2 is written in terms of species D, and reaction 3 is written in terms of species E. So for each of these reactions, we need to write the relative rate of the other species involved in that reaction. So for reaction 1, we need to write relative rates for B and C. For reaction 2, we need to write relative rates for C and A. And for reaction 3, we need to write relative rates for D and C. So let's do that. All right, so relative rates. So let's start with reaction 1. So we're going to write for B and C. So R1B is going to be equal to negative 1/3 R1A. And how I'm getting that, if I go back here, we want to use the equation of relative rates, which is to take the relative rate for any species divided by its stoichiometric coefficient divided by, or is equal to the relative rate of another species divided by its stoichiometric coefficient. So for example, in reaction 1, if I want to determine what the relative rate of reaction, or the relative rate of B is with respect to A, I would say R1A divided by -3, because that's the stoichiometric coefficient on A, and it's negative because it's a reactant species, is equal to R1B divided by 1. So in the case of B, it's a product, so its stoichiometric coefficient is positive. So then I can solve for that. Therefore, R1B is equal to negative 1/3 R1A. And I can do that for all of the different species. So for example, R1C is going to be equal to R1B because B and C are formed in the same ratio in reaction 1. Okay, so if I go through and do that, I'll have R2C is equal to negative 2/3 R2D R2A is equal to negative 1/3 R2D. R3D is equal to negative 4/3 R3E, and R3C is equal to negative R3E. So that should be the relative rates. So now I can fill these into the net rates, and now I have mole balance expressions, except for all of these rates are functions of concentration, so that would mean that I need to have concentration equations. So going to write those down, and as you see, we've already developed more than our 10, the 10 allowed explicit equations that we could have used. If we had fewer than that, we could use Polymath Plus free online solver, but we've already gotten more than that, which is why I'm going to use Python in a minute. Okay, so our concentration equations, we're used to using those, writing the change in the concentration due to the change in the number of moles. So this is actually a change in the volumetric flow rate, but we're going to bury it into the concentration term. We're used to doing this as the progress of you're using conversion as the progress variable. We can't do that here because, again, we're not solving in terms of conversion. So we need to use the more general equation written in terms of molar flow rates. So that equation is C, the concentration of any species J, is going to be equal to the total concentration initially, CTO, times the flow rate of that species divided by the total molar flow rate. That total molar flow rate is going to be progressing as we go through, as the reaction is carried out. And then that's going to be multiplied by, and hold on, I'm looking up. I want to make sure I get the terms correct. The pressure divided by the initial pressure, where again the pressure, the numerator there is the pressure at anywhere along the length, along the progress of the reaction, and then T divided by T naught. So this is a general equation. So here, these actually cancel out, or they go to 1. So this goes to 1, and the reason is no pressure drop. And then this goes to 1 because it's an isothermal reaction. So we're not going to deal with pressure drop in this class. However, we'll deal with non-isothermal reactions coming up very soon. So then I have my equation that I'm going to use. Cj is equal to CTO divided by, or times Fj divided by Ft. So I need an equation for Ft. That's simple. That's just the sum of all of the molar flow rates. The molar flow rates I'm solving for through my mole balances, so that's really all I need there. And then I can write my concentration equations for each of the different species. Oops. All right, so then I should have all of the equations I need. So now I can put this into a solver and solve it. So let's do that. All right, so here I have the Python file set up for this problem that we were working on for multiple reactions in a PFR. So up here I just have the normal information that I need to, or the normal information I need to use to import the correct modules into Python. So I'm going to run that. Here I have constants. So we said that the inlet concentration of A is 0.2 molar. A is the only species fed, so that's also equal to the total concentration. And the volumetric flow rate coming in is 100 moles per minute. Now, this is a gas phase reaction with a change in the number of moles, so that's going to change over the course of the reaction, but the inlet value is given. Here we have, we're going to need the inlet molar flow rate of A, and we can use the concentration and the volumetric flow rate to get that. And then these are all the rate constants. I don't have units written here, but all of the units are moles are moles. Volume we're using cubic decimeters or liters. Time we're using minutes. So as I've written down these constants, I've made sure that they've all been converted. The reactor has a volume of 400 cubic decimeters. That's this value, and this here is setting up the integration space for the volume variable. Okay, so I have here the function that I'm going to use to solve for this. I've called it PFR. Really, I can call it anything I want. Let me go back here and run these constants. Okay, the function is going to be of two variables. I've used a generic variable z and then the variable v. Again, those can be anything. The variables that I'm going to write in terms of the dependent variables are going to be the molar flow rates. Listed those here. And now I can start to define my problem. So I've started out by defining my concentrations, which are functions of the molar flow rate. We said we needed the total molar flow rate, so I've written that equation in, and then basically written the concentration equations, which are in terms of the molar flow rate of each species. The rate laws I basically copied those in from the problem statement. Thing to notice here, in Python, the syntax for raising something to a power is 2 asterisks. So this right here is equivalent to the caret symbol. Python isn't going to recognize the caret symbol as raising to a power, so I have to do it that way. These are all my relative rates. So as we wrote out, from the relative rates, I can then solve for the net rates of generation, and then I can use that to set up my interdependent ODEs. These, again, I'm calling these DFA, DV, but I can use any sort of name. Python doesn't know chemical reaction engineering, it only knows math, and so it's basically just asking us to define an equation or a differential equation. All we got to do is do that. I like to label these, or I like to give these the names of things that I'll recognize because it makes troubleshooting easier. Okay, so now this is how I couple them. I set these equal to this vector here, or this, I guess, grouping of equations. I've coupled these, and then I can use this syntax. For the initial molar flow rates of each species, A is coming in, nothing else is, so the rest of those are 0. And then this is the code that I'm going to use to integrate the ODEs. Once I'm done with that, I'm going to need the code to report back to me the values I need. I'm going to need the flow rates of all the different species. What I've done here is generated a matrix of values. The matrix has 5 different vectors, 1, 2, 3, 4, 5, one for each species, and each one of those is going to have the molar flow rate of that species as a function of the volume. So this is how I tell the matrix I want to pull out each one of those vectors and assign it to one of the different flow rates. They're going to be the same order as I've listed up here. All right. Once I have those values, now I can just write algebraic equations, so I'm going to do that. I have my total molar flow rate. I'm going to rewrite my concentration equations. I, of course, wrote them up here, but this is a function, and all this function really gives us is these molar flow rates. So if I want those again, I'm going to have to write code to recapture them. Now I'm going to want, here's the equations for my cell activities. I'm looking for these cell activities with the tilde. What that it gives me is, or what that is the exit molar flow rates of the different species. I can use this term -1 here. If I put the argument in a vector as -1 in Python, that gives me the last value in the vector. So that's perfect. That's exactly what I want. And then I can plot my different species. I'm going to plot all of my different concentrations, and then I'm going to print out my selectivities. And you can see I've already done that, but let me run the function. Here I get my graph. So we see as the reaction runs, the concentration of A is decreasing. I have a appreciable generation of species B and C. Species D and E, I don't get very much of those. I could probably zoom in lower on the plot and see, are those values 0 or are they just very small? If I go back to my reactions, actually I would need to go back. Yeah, I can't do that here. I would need to go back to the problem statement to do that. I don't want to switch here what I'm doing, But if I go back and look at that, basically I'm feeding A, and then I have a series of reactions to form D and E. Those reactions aren't getting, they're not making much progress because they rely on species that are formed in order to run. So, for example, for the second reaction to run to form D, C needs to be formed. Now we see C is forming here, but in addition, as soon as D is formed, it's reacting to form E. So those reactions don't run as much, and I don't get as much of those species. If I look at my selectivities, I actually am forming more E than D, so all of the D that's getting reacted is going, or all of the D that's getting reacted is going to form E. And if I look at my formation of C to D, I'm getting a lot more C than I am D. So my C is forming, my D, I'm not getting a lot of D, and that's probably because D is reacting as soon as it's forming.